In the early 1800s, the world changed forever. Steam engines roared to life, factories multiplied, and for the first time, machines began to outpace muscle. The Industrial Revolution didn't just transform economies, it rewrote the very fabric of society. Nations shifted from agrarian to industrial powerhouses, and with that shift came a new dependency, not on crops or kings, but on engineering. But as machines grew in size and speed, something unexpected started to happen. Metal parts began to crack, not from a single heavy load, but from repeated use over time. Bridges collapsed, trains derailed, and for a while, no one really knew why. This was the dawn of a new field in mechanics, fatigue, a phenomenon that would force engineers to rethink everything they knew about strength, safety, and how materials behave under repeated stress. And it's not just a problem of the past. Dramatic failures still happen today, like the 1988 Aloha Airlines accident, where a section of the fuselage tore away mid-flight due to undetected fatigue cracks in the aircraft's skin. Incidents like these remind us that fatigue is not an old problem, it's a persistent one, and understanding it is critical for any practicing engineer. In today's video, we'll start with the historical roots of fatigue and then dive into the modern tools engineers use to analyze it. We'll break down stress life, strain life, and the linear elastic fracture mechanics approach, and then discuss when each is the right tool for the job. So without any further ado, let's get into it. Alright, hello and welcome back to our machine design series where we're talking about fatigue failure analysis today. So all that I've written here is just a summary of the bullet points from the introduction of this video, just so that you have something to keep in your notes. And now let's move on to a sort of comparison of engineering design before and after the Industrial Revolution, and I think this will really make it clear why fatigue became a real issue after the Industrial Revolution. All right, let's fill in this table. So on the leftmost column, we have some typical characteristics of engineering design. In the middle column, we're going to list out those characteristics prior to the Industrial Revolution, and then on the right column, we will list out those characteristics after the Industrial Revolution. So, prior to the Industrial Revolution, we had engineering design that was primarily based on static loading. Our speeds are relatively slow, our loads are light, and our factors of safety are large. Typical power sources prior to the Industrial Revolution would include the water wheel, and a water wheel might cycle, let's say, a maximum of about 10,000 cycles per day. The materials that were used for construction of engineering designed machines would include things like wood, stone, and simple metals. So unprocessed metals, think of things like iron and copper. Again, speeds are relatively slow, probably less than 10 RPM typically. And the loads are relatively low. Maybe a few kilonewtons. And our factors of safety were higher. Somewhere between 5 and 10 would be typical, and that's due to material uncertainties. So when you have more uncertainty in your design, typically that means you need a higher safety factor so that when you're on, let's say, the low end of possible yield strengths, you still have some margin of safety left over. Okay, so that's prior to the Industrial Revolution, and then everything really changed upon the introduction of the steam engine. Which was a typical power source after the Industrial Revolution. And with the development of the steam engine, shafts were expected to run faster, accumulating high repetitions of dynamic and cycling stresses. So a steam engine shaft, as compared to a water wheel shaft, is going to experience many more cycles. It could accumulate more than 100,000 cycles in a day easily. Materials that were used for construction of the steam engine and for other engineered products in this time period, which includes the time period that we're currently living in, includes things like steels, alloys, concrete, other advanced metals, and plastics. And of course, there's more. Speeds after the Industrial Revolution would often exceed 1,000 RPM, or do often exceed 1,000 RPM. You can prove that to yourself by taking a look at your dash in your car to see exactly how many revolutions per minute your engine is cycling, and I can tell you it's going to very often be in excess of 1,000 RPM. The loads after the Industrial Revolution are relatively high, typically. Of course, there's exceptions. And we're talking about hundreds to even thousands of kilonewtons. And then we have lower safety factors typically. Around 2 to 3 would be a common safety factor. Of course, that is application specific. But just speaking in kind of generalities here, we've lowered our safety factors for most applications because we have improved material reliability. And I'll just throw in and other engineering advancements. Okay, so as we improve material manufacturing processes, we get steels and other materials with higher strengths and greater uniformity. So when we have higher reliability, more uniform materials, we get greater confidence in our design for higher stresses and lower factors of safety. However, once we did this, we increasingly saw machine members failing suddenly and often dramatically under these fluctuating stresses. So a key characteristic of these failures that were observed was that it was happening in applications where there were many, many cycles per day. And so the common wisdom at the time that this phenomenon was first being observed was sort of, well, the materials are just getting tired. They're experiencing so many repetitions of these loads that they just fatigue. And that's where the term fatigue comes from. But actually, the material itself is not changing. What I mean by that is the material properties are not changing. So if you take a failed part that has experienced fatigue failure and test its material properties, you'll find that they're the same before and after the failure. What's actually happening is there are cracks or defects that are starting cracks that eventually propagate to failure after repeated cycles. So there has been a lot of research in this area since the start of the Industrial Revolution, and the development of fatigue failure analysis techniques continues to advance. This is still a very active area of research. And so it's a very interesting topic for us to study. You'll find that as you continue in your education, you will learn topics closer and closer to current day. So we have now entered the turn of the 19th century in your engineering education. And if you go on to graduate school and PhD research, then you'll be on the forefront of, the 2020s today. Anyway, so the development of fatigue failure analysis techniques continues to advance, and there are three major types of fatigue analysis that we're going to talk about today and compare to try to understand when it is appropriate to use each one of them. All right, first of all, let's think about what our goal is with fatigue failure analysis. So the goal of any fatigue analysis is to predict really two main things. First of those is the number of cycles to failure. So as an example, how many times can I compress and then relax, or how many times can I compress and then relieve and compress and relieve a spring? How many times can I maybe lay down on my mattress until the springs start to experience a fatigue failure? Now, there may not be an exact number of cycles to failure. We may be able to predict that a machine component is expected to have an infinite life. Okay, so our goal is to either predict that our machine component can have an infinite life, or if not infinite, then how many cycles will it take to fail. One important note that I always like to have accompany this infinite life talk is that there are some prerequisite conditions to being able to predict infinite life. And also, of course, this is a theoretical idea that we can have a machine component experience infinite life. And all of fatigue is sort of stochastic and random in nature. So even components where we predict infinite life need to be regularly inspected to make sure that they are still performing. And another caveat to this is that there are certain materials that will never be able to have an infinite life. For example, aluminums do not have an endurance limit, and therefore you can never predict an infinite life for a machine component made out of aluminum. Steels, on the other hand, do have an endurance limit, and so you may be able to predict infinite life for machine components made out of steel. Now, as I said earlier, there are three major types of fatigue analysis, which we can use to predict the number of cycles to failure or infinite life for a component. All right, so I'm going to set up a similar table as we had above so that we can compare some of the typical characteristics of each of these three types of fatigue analysis. Let me build up that table and then we'll be right back. All right, so first of all, what is the design goal? For any problem that you're tackling, that's going to be one of your first questions, right? What's your design goal? If your goal is a damage-tolerant design, meaning you're going to assume that you have some starting flaw size, maybe on the order of microns, and you want to understand how big of a defect your design is going to be able to tolerate. If that's your design goal, then linear elastic fracture mechanics is probably a good method to start with. And when I say linear elastic fracture mechanics, I'm talking about the method we discussed just in the last video, although that one we only discussed static loading. You can take that same framework and apply it to fatigue. All right, now for the strain life method, our design goal when using this method is typically going to be to predict a safe life. So this means we're going to be predicting a particular number of cycles to failure most often. Whereas with the stress life method, we are going to typically be looking for infinite life. We can also use it to predict the safe life, so the particular number of cycles. And usually you will use the strain life method for lower cycle fatigue and the stress life method for higher cycle fatigue. So if you're expecting to be on the order of, hundreds of thousands of cycles, then you'll typically use stress life method. If it's going to be under, say, 10,000 cycles or so, you'll more often use the strain life method. And there's still active debate in the field on what defines low cycle versus high cycle fatigue, what that exact number of cycles is that distinguishes the two, but around 10,000 cycles is sort of where the consensus lies. Okay, next up, let's talk about typical applications. So a typical application for linear elastic fracture mechanics is aerospace. Aerospace industry uses linear elastic fracture mechanics quite often, and this is because they are very often doing inspections with ultrasonic equipment, measuring flaws that exist in components, and then they want to understand whether that flaw size is acceptable. So they're very often operating with a damage-tolerant design. For the strain life method, a typical application would be energy, especially in high temperatures. And this is because the strain life method is good at dealing with plastic strains. So if you have high temperature applications where you're going to be experiencing creep or any other type of plastic deformation, then strain life method is going to be able to handle that most effectively. Now the stress life method has a lot of applications. It's the simplest method to use. It is the most established method, and it is very widely applicable. All right, so now let's talk about some of the advantages of each, and then we'll talk about the disadvantages. All right, so advantages of linear elastic fracture mechanics are that it is fairly accurate in predicting crack propagation of a pre-existing crack or defect. And then let's go ahead and do disadvantages because this leads us right to it. So the main disadvantage of linear elastic fracture mechanics is that it requires knowledge of the crack size, shape, and location. All right, so now how about the strain life method? The strain life method, big advantage is that it considers plastic deformation. And this makes it really good for low cycle fatigue. And a really good example of low cycle fatigue would be like taking a paper clip and bending it back and forth a few times. Each time you bend that paper clip, you're going to get some plastic deformation, right? So it's not going to immediately return back to its original shape. And it's also going to take several cycles before you achieve failure of the paper clip, before it actually breaks and comes apart. So if you were going to try to analyze that fatigue failure of a paper clip, you'd probably want to use the strain life method. Now let's talk about the disadvantage of this, which is that it is a pretty complex method to use, pretty complex analysis, and it requires detailed material data. So for example, with the paperclip, I need to know not only what is the yield strength of that material, but also the rest of the stress strain curve after yield. So I need to be able to predict exactly how much plastic strain is going to be in the material after each cycle. And if you were talking about high temperature applications, then you need stress strain curves at those high temperatures. So you can see that it starts to get fairly detailed fairly quickly. All right, now as far as advantages for the stress life method, actually I wrote that above. Sorry. So the advantages of the stress life method are that it is the simplest, most established, and very widely applicable method. I meant to write in the application section that this is just used very generally on rotating equipment. Okay, so stress life method, simple, very well established, and widely applicable. The disadvantage of the stress life method is that it does not account for plasticity or microstructure. In other words, the stress life method does not account for any plastic deformation of the material, and it does not account for any starting defects or cracks. All right, so last category or last characteristic, just want to give a little bit of an indication on when each of these methods will work best. Linear elastic fracture mechanics works best when crack growth is critical. Okay, this is why it's very often used in aerospace applications. When a crack reaches a certain size, we want to know so that we can take that airplane out of service and repair. The strain life method works best when a material is undergoing significant plastic deformation. And lastly, the stress life method is going to work best when your material is subject to low stress, high cycle fatigue. Okay, so for this class, we're going to start with linear elastic fracture mechanics, but we will discuss each of these three methods in some detail, giving the most detail to the stress life method in the end, because it is so widely applicable and widely used. All right, so that wraps it up for this video on an overview, an introduction to fatigue failure. We talked about the characteristics of loading. We talked about the three major types of fatigue analysis and when each is most applicable or works best. And we talked about just a little bit of motivation for developing these methods with the Industrial Revolution and the history behind that. So In the next video, we'll get into linear elastic fracture mechanics, using that for fatigue analysis, and then we'll discuss the strain life method a little bit. We won't go into too much detail because, as we said earlier, that gets very complex very quickly, and then we will focus a lot of our attention on the stress life method. So, hope you're looking forward to all of that. Thank you for watching, and I'll see you in the next one.